Okay. So we just talked about our paired samples or our matched pairs as one way to look at two samples. But again, many times, even though paired samples would be our ideal, lots of times it just can't happen reasonably or practically, and so we're just going to go with independent samples. So again, remember, independent samples means there's no relationship between the measurements in one sample and the measurements in another sample. So things like one person can't be in both samples for it to be independent. Okay. Now, independent is still good. We still want, if we can't have paired samples, our next best thing is independent samples. Because we hope that if we just randomly choose people and we put them in each group, that we can eliminate a lot of that bias. So half the old people might manage to be in one group and half the young old people will be in the other group. Just by chance, hopefully it will be at least fairly close. Because we're going to deal with two different populations, we do need some notation. So we could have population X and Y, or 1 and 2, or A and B. Okay? And we'll have a mean for each one, population standard deviation for each one, sample size for each one. It's easier to write n and n than it is nx and ny, usually for all of our formulas. X bar and y bar, and sx and sy for our sample standard deviations. Okay, so we'll just throw that in, so we just have to somehow differentiate between the two populations. Okay, so an example is we have a bank manager who's developed a new system to reduce the time customers spend waiting to be served by tellers during their peak business hours. So we can think of population 1 as the waiting times of the current system. So he could, on the first day, he uses the current system, he randomly selects 100 customers and finds that the sample mean waiting time is 8.79. Now population 2 could be the waiting times of the new system. So second day he could use a new system, randomly select, say, 80 customers and find that their sample mean is 5.14. Now, at this point, could there still be some bias if he only looks at people on one day and people on the other day? Okay, yeah, I can still see some bias. Maybe he should do it for a week or so and do morning 1, use the old system, and the afternoon use the new system, and then the next day switch it up and do morning new, afternoon old, and then morning new, afternoon old. Something like that. Maybe you could switch it up to try and get rid of some of that bias. But that's his current setup. Okay. And really, our overall goal here is we want to compare the population means for mu x and mu y. To do this, we're going to look at the difference in the mean, so mu x minus mu y. So what would be a good estimate of mu x minus mu y? How would you estimate the difference in the population means? Based on everything we've done, when we wanted to estimate one population mean, we use the sample mean, right? So if we want to estimate the difference in the population means, we could use the difference in the sample means. To estimate the difference in the population means. So if I want to look at the difference in the sample means, that would be x bar minus y bar. I only wrote x bar first because it came first in the alphabet. So let's look at some of the theory for our sampling distributions. So consider randomly selecting a sample of n measurements from a population that has a mean mu x, variance sigma squared x, and let x bar be the mean. And again, a sample from our second population, sample of m, we have the mean for y, variance for y, and the sample mean of y bar. Okay. Now, when you think about it, if I took different samples from my first population, for every different sample I took, I would get different values of x bar, correct? Okay, and that's why we have our own sampling distributions for x bar. It has its own mean, it has its own standard deviation, because you have all your possible values of x bar. Well, you could get different values for x bar, but you could also get different values of y bar for the different samples in that population. So therefore, based on which sample you pick, you could also get different values of x bar minus y bar. Okay? Because based on which sample, you get different values of x bar, different values of y bar, so you get a different difference. So x bar minus y bar is its own random variable, and it has its own sampling distribution for all the possible values. So the sampling distribution of x bar minus y bar. If the randomly selected samples are independent of each other, then the population for all your possible values of x bar minus y bar is going to have a normal distribution if either both populations are normally distributed or both sample sizes are at least 30, or one is normal and the other has n at least 30. Okay, so somehow you have to have this combination of they're either both normal or both sample sizes are at least 30, or one is normal and the other one is at least 30. So you have to check this condition for both samples. Now the expected value of the mean, so the mean of x bar minus y bar, okay, will just be the mean of x minus the mean of y. Okay. And the standard deviation, remember how the standard deviation for one sample is sigma squared x over n, and then take the square root for the standard deviation? Okay. So if we have 2, then it's just variance of x over sample size plus variance of y over sample size, and take the square root. Okay, and that's just going back and using all the rules for expected value and variance that we've learned in this class. Now you may not remember, but I said once that our test statistic usually follows this form. So estimate minus hypothesized value over the standard deviation of the estimate. Okay. So let's say we want to know if the difference in the unknown population means is equal to, well, x bar minus, or mu of x minus mu of y. We're going to call it delta. Okay. So that's the difference in my populations that I'm looking for, and the difference in the population means. So I might ask something like, is there a difference? Which means that you just want to know if the difference is 0 or not. Or I might say, is the difference at least 10, in which case delta would be 10, etc. Okay. So what is our appropriate test statistic? So first of all, my estimate. Well, what is my estimate of the mean of x minus the mean of y? My estimate of that is x bar minus y bar. Okay, minus my hypothesized value. My hypothesized value is if I want to know if the difference is delta or something greater than delta, less than delta, not equal to delta, etc. So my hypothesized value would be that delta. And the standard deviation of the estimate, what's the standard deviation of x bar minus y bar? Okay, so I just told you that it would be the variance of x over its sample size plus the variance of y over its sample size. So this would be our theoretical test statistic. Why might I say the theoretical test statistic? Versus like the test statistic that I might use on every test. Because it does have sigma as my population standard deviation, and in practice, do we usually know the population standard deviation? No. And so this would be my theoretical test statistic. But we might not always know what my standard deviations are. So we might have to estimate them. Okay. But that's what it would be. Now, in practice, delta is usually 0. So usually your boss will just ask, is the mean for A greater than the mean for B, or less than B, etc. And if that's the case, then the difference is just, the null hypothesis difference would just be 0. And if it's 0, then it just disappears from the formula. So here are our two sample tests for mean of x and mean of y. So we want to compare two population means, and we have independent samples. So the populations are normally distributed, or both sample sizes are at least 30. Okay. The null hypothesis, okay, is just that the two means are equal, or you could say that mu of x minus mu of y is equal to 0. Okay. So this is the more technical way to write it, because I could then also say equals to 1 or 2 or 3, but almost always it's just going to be an equals, and so we prefer to write it as just mu x equals mu y. It makes it a little bit simpler for us. So for our two sample z-test, okay, so if we know our population variances for some reason, then our test statistic is x bar minus y bar over the square of the variance of x over n plus the variance of y over m. Notice because we're using our population variances or standard deviations, we're using a z test statistic. Now, if I ever don't know my population variances, we have to switch to a t-test. Now, for two samples, there's actually two different t-tests that we could use. Okay, so a two-sample t-test with equal variances, sometimes called pooled variances. Okay, so this happens if you don't know the if you don't know the population variances, but for some reason you think that they are the same. Okay, then you can use this test statistic. So t is, again, the difference in the sample means over the square of your pooled variance times 1 over n plus 1 over m. Okay, where your pooled variance is equal to this fairly complicated looking thing. Okay, and you use your t distribution with degrees of freedom of n plus m minus 2. Okay, so they've done all the work, they've proved that this has the t distribution. Okay, the reason that you would want to use equal variances, if the variances are equal, okay, this test has higher power. Anyone remember what power is? Power is the probability of rejecting a false null hypothesis. So if the null hypothesis is false, you want to reject it. So power is a good thing. You want higher power. Okay, so if the variances are equal, then this test is a good thing because it will have just slightly higher power. Okay, it'll be just a little more accurate. Okay. Now in practice though, if you don't think that they're equal or you're not sure, then you can use what's called the two-sample t-test for unequal variances. And in practice, lots of people say, well, if I'm not sure, I'm just always going to use this one because then I know I'm safe. Okay, so it's always safe to use, but if the variances were equal, then the pooled test has just a little more power, which is good. But this version is always safe. It will always still give you safe results. You don't have to worry about it. Okay, so again, if you don't know the variances, but you think that they are not the same, then use this test statistic. Notice my test statistic looks a little bit simpler. Just x bar minus y bar over the sample variance of x over n plus the sample variance of y over m. Looks very simple until you get to the degrees of freedom. So use a t distribution, but you have to use what's called a satterthwaite approximation for degrees of freedom. And there's your formula for that. Okay, not so simple or nice. Okay, but that's what it is. Learn to put it in your calculator quickly, or use an online calculator or something. On your homework, if you looked at it, you might notice that I put in a document up there that has the degrees of freedom and pooled variance for a lot of your problems, so you only have to find it like 3 or 4 times, and then after that I've given it to you to save you some time. And finally, what might your p-value look like? Okay, so if I have the alternative hypothesis that the mean of x is greater than 0, which we could also write as the mean of x minus the mean of y is greater than 0. So it could be written like that. I just prefer to write it the first way. I think it makes a little more sense. But anytime you have this greater than, then your p-value would of course be the area in the right tail. If you have the mean of x is less than the mean of y, so mu x minus mu y is less than 0, then it would be a left tail. And finally, if you have the mean of x minus the mean of y is not equal to 0, or if you just have not equal to, then you would want the p-value to be the area in both tails. So let's try one. Okay. So suppose a sample of 100 waiting times is observed under our current system, and it gives a sample mean of 8.79, and then a random sample of 80 waiting times observed during the trial run of the new system yields a sample mean of 5.14. Assume that somehow we know these population variances. Conduct a hypothesis test to see if the new system reduces waiting times. Use alpha equals 0.05. Okay. Now, one of the things that I like to do on this, which means that makes more sense than trying to memorize all my symbols, is write out a table. So, old, new, so I'm going to need a little more room. And I might put something like the sample size, sample mean, and let's see, they told me the population variance. So my old sample size was 100. The mean was 8.79, population variance was 4.7. Okay, new sample size, or sample size for the new is 80, mean for the new is 5.14, and variance for the new is 1.9. So I just like to put it in a table like this just because I do have a lot of little subscripts throughout the problem. But let's start this off like we would any test, which means I need a significance level. They told me to use alpha equals 0.05. I need to check my assumptions, okay, which is both populations are normal or both sample sizes are at least 30. Okay, so in this case, both sample sizes are at least 30. And for my null and alternative hypotheses, okay, for the alternative first, they want to see if the new system reduces the waiting times. Now, I did write down old and new, so I wrote down old first, so I'm going to want to compare mu for old and somehow compare it to mu for new. Not that they had to be in that order, but that was the order I wrote them down in, so once I pick an order, I stick to it. So I get the same result, the correct results. Okay, so for the null hypothesis would be that the means are equal. Status quo, means are equal. Whereas the alternative, we want to see if the new system reduces the waiting time. So if it reduces the waiting times, mu for the new should be less than. So mu for the old should be greater than. Okay, if you want, they did use x's for the old, so I could write this as mu x is greater than mu nu. However, I prefer to write it in a little more context, and I'll just write old and new because it makes more sense to me throughout the rest of the problem. Okay. So null and alternative hypotheses. What else do we need? Next up is my test statistic. Will this be a z or t? Z. Because we know the population variances. So z is x bar minus y bar over the square root of sigma squared x over n plus sigma squared y over m. Now again, you can go through, you can memorize the subscripts, and you can match everything up. Or you can just remember, if I wrote down old first, then I keep old first throughout the entire problem. So what I mean by that is now I'm just going to look at my table. I'm like x bars and y bars. Those are my sample means, which is 8.79 and 5.14. Which one do I have to put first? The 8.79 because it was the old, and I said I was going to do old first. So 8.79 minus 5.14. Okay, square root, so variances. So this is now commutative, so the order doesn't matter as much, but I'll still keep doing old stuff first. So variance of old, and it looks like they did tell me variances originally and not standard deviations. So variance of old is 4.7 divided by its sample size, which is 100, plus the variance of the new of 1.9 divided by its sample size of 80. Now, did anyone put this in their calculator already? Go ahead and start. $13.72. Anyone else? That seems really big. I'll see you got two. So that's my test statistic. Now I need a p-value. So here's my 13.72. I'm looking for the area in the right tail. And without even looking at that z table, what's that area going to be? Very, very small, right? Because if you look at your t table or z table, it only goes up to 3.4. And at this moment, the area to the left is 0.9998, so the area to the right is 0.0002. So by the time we get to 13, we are at essentially 0. So my p-value is essentially 0. So small p-value, reject the null hypothesis. And we have extremely strong evidence that what? What did we show here? So we showed that we reject the null hypothesis, so we showed that the mean for the old is greater than the mean for the new. Okay? Now your boss asked you specifically, does the new system reduce the waiting times? So we showed that the mean for the old is greater than the mean for the new. So how could you phrase this in a way that is technically correct for your statistics teacher and makes sense to your non-statistical boss?
The average waiting time on the old system is greater than the average waiting time.
So average time on old system is greater than average time on the new system.
Can you also say that the average time on the new system is less than the average time on the old system? system?
And I probably would have phrased it that way to say the average of the new system is less than the average on the old system just because it would fit a little more with what the boss specifically asked. But either way, we get our same point across. So we believe that the new system does reduce the waiting times. Do we know how much? No. So if we did a confidence interval, then we could actually tell them how much we think it reduces it. But at this point, we're extremely sure that it did reduce the time. Yes?
So we knew that the p-value was to the right because the first, we phrased our alternative hypothesis, the first name was greater than the second.
Uh-huh. Yes. Yeah.
That will always hold true as long as you follow that when you're calculating your testing.
Yep, so as long as you're consistent, so because I did old greater than new and I wrote it that way, I had to go to the right tail. What would have happened if you had been doing this test and instead you wrote mu for new greater than mu for old? How would it change the rest of your problem? So if you'd written, so don't write this down, I'll erase it out before I post it. So if you'd written mu for new minus mu for old, okay? So what would change step by step? Well, when you got to this case, then it would be the mean for new minus mean for old. So we do 5.14 minus 8.79. But what's the only thing that would change in that calculation? Just your sign. So we'd get a negative 13.72. So when you go to find the p-value, you're at negative 13.72, but because we did a, so I meant to say less than, you would have to shade to the left, but your area would be the same. So your p-value is the same, your conclusion is the same. Everything works as long as you are consistent. Okay. Other questions here?